Hello. Hello. This is IDC 451 seminar delivery paper presentation. I am Abhin Sundar from Department of Physical Sciences and my topic of presentation is a study of light curves of X-ray flares. So this is the paper that I have referred to for making this presentation. So outline of my presentation. So what I'll describe is, so I'll introduce you to what are X-ray flares. So here is what you see is the binary star system where the companion star is shedding of its material to the this neutron star or pulsar, which results in formation of an accretion disk where the thermonuclear outbursts take place. This results in formation of X-ray flares. Then I'll I'll try to will try to generate and see how the light curve of these X-ray flares are. We'll also try to model these light curves and then we'll analyze these light curves and see what results we can obtain from all these light curves. And then I'll conclude my presentation. Okay, so something about flares. So flares are events in which large amount of energy is released in very short interval of time. Okay, so if you see there is this is the formation of highly energetic magnetic loops where plasma is confined, and since it is heated to a very high temperatures, so it results in a high amount of mass and energy release. If you see here, so there are two types of flares, X-ray flares, short decay flares and long decay flares. Short decay flares are basically less than 1 hour, and long decay flares are more than 1 hour. We can classify these accordingly. So short decay flares, they may be maybe seconds or maybe tens of seconds, maybe milliseconds. So they are very short, pretty short. So these flares are analogous and they are similar to solar flares. Okay, so in solar flares, what we see, we can get information about sunspots, active regions of the sun. So similarly, we study the stellar flares so that we get information, all these information about them. So we can also classify them according to the what type of stars they are and what position they take in the HR diagram. Okay, so what are these light breakups and why they form? So basically, these, as I said in my first slide, that this is a formation of accretion disk, which results and which is actually responsible for these generation of X-ray curve, X-rays, due to thermonuclear outbursts at the neutron star surface because of this formation of X-ray, because the formation of accretion disk, as I said earlier. So what we do is we bin the time scale. We bin the time scale like if we take 60 seconds, so we divide into 3 seconds, for example, and then we see how much count rate we are actually getting in this time interval of 3 seconds. It is basically these curves are basically characterized by a rapid rise in intensity followed by a gradual decline. I'll show you in a bit of moment how this looks like. So it is very important to keep monitoring X-ray sky for such outburst phenomena for these sources because we get a lot of information from these kind of sources. So this is how it looks like. As I said here, that it is characterized by rapid rise. If you see in this region, there is a rapid rise followed by a gradual decline. If you see, this is called like an exponential decay kind of stuff. And if you want to read more about this, here is the reference. You can go through it. So now we'll model these light curves. So this fast rise exponential decay, it is also known as FRED. This FRED model was chosen as an appropriate model for these thermonuclear outbursts to model these X-ray flares. So there was this person called Norris. He generated, he classified and he studied all these flares and then he came up with a solution. This is called a Norris function. If you see here, all these parameters, A is the amplitude, lambda is defined by this quantity where I've shown here. TS is the start time of the flare, and tau 1 and tau 2 I'll describe in a few moments. So this is the function which is used for modeling these binned light curves. So okay, now coming to tau 1 and tau 2, tau 1 and tau 2 they are responsible for rise and decay part of the curve. So basically they characterize rise and decay part of the modeling curve, and this is how it looks. If I zoom in, if you see here, yeah, this is how it looks. So initially it wasn't modeled, but now it is modeled. It looks great, right? So this is the original paper of Norris. You can refer to here for more details, how he did that, how he analyzed it, and how he came up with this solution. So now we'll analyze what results and what sort of information we can obtain from these things. So there is one thing. There is a periodic behavior of light pulse from time to time. That was that the last slide I showed. That was one pulse. It may happen that this pulse is periodic, like there are many binary systems, or there are some other stars which actually are periodic, which shows this periodic behavior. So we get a lot of information from that. So there's a saturation level for this flaring activity, the maximum, and it depends on mass of the star. It does not depend on anything, but directly proportional to the mass of the star. Okay. So what we do is we plot luminosity curve, and then we find the change in flare luminosity. We find that this change in flare luminosity is due to change in flare frequency at each energy level. Okay. So active stars, they flare more often at every flare energy level. So they flare more, and their flaring frequency is more. This activity, it depends on parameters like volume of the convection zone and the stellar rotation. So these two properties, we can generate a lot of information from this. That young pre-main sequence star, I'll show you in a bit a moment where this young pre-main sequence star and what they are and where it lies. So they are rapid rotators. They have this property. They are fully convective, and they have large volumes. And this is the reason why their activity is very much more than as compared to other stars. Secondly, binaries. So what happens in binaries is the tidal forces, they tidal forces have locked their periodic rotations, which give rise to this synchronization effects. So one of this binary class is this RSCVN class of binaries, this class of stars, which actually show this kind of result. So they have very high amount of active, they are very highly active, and their activity is more. So let's see conclusions, what we conclude from all these stuffs. So if you see here, this is the HR diagram. This is the absolute magnitude versus the color. You can also plot this as luminosity versus temperature scale. Both are fine. So what we conclude is, if you see there, flaring stars lie on or above the main sequence. This includes, as I said earlier, young as well as evolved stars, singles and binaries. This I told earlier. So this, if you see this line, this is the main sequence line. Okay. So so all these stars which show flaring activity, they lie in this region. Either they lie in this part. So young main sequence stars is, this is the main sequence line, and they lie all in this region. Sun actually belongs to very much near the center. It has luminosity 1 and temperature of 5000 Kelvin. So it somewhere lies near the at the center of this main sequence. So what we conclude is timescales of energetic flares are longer than smaller flares, irrespective of host star. I said earlier that this is directly proportional to the energy is directly proportional to the mass of the star, directly proportional to. Okay, so time scale of this energetic flares. So as I said earlier, there are two types of flares, long and short. So basically, this is the reason why flares, long decay flares, they have more and they are more energy than as compared to other stars. Secondly, the flare occurrence. So if we plot the flare occurrence as a function of time, we get two types of, either we get Poisson or either we get periodic components. So anything we can get. As I said earlier, atmospheric activity or the flaring activity, it grows with increasing volume. It is proportional to volume of the and it is proportional to the convective envelope of the host star. Right. So we get this information as I proved earlier in the last slide. So for more information, you can actually go through this brilliant paper by B.R. Patton. He shows all these stuffs like stellar flares and the characteristics. So these things, this is the reason why we study X-ray flares. We get a lot of information from this. And like in the case of sun, we get the information of sunspots, and no, it directly affects our life. So similarly, we can actually do it for all the other stars. There are many stars which show this flaring activity, thermonuclear outbursts, and all this phenomena which is happening in the universe. Okay, thank you for listening to me. Thanks a lot.